Good morning, friends. In exercise of chapter 15 waves up to the 15.10 numerical we discuss. Now next numerical 15.11, the transverse displacement of a string tied at both ends is given by the equation y xp is equal to 0.06 sine 2 pi by 3x into cos 120 pi t. There is the equation of the transverse wave traveling in a string tied at the both ends. Here the x and y are in meter and time t is in second. Length of the string is given the 1.5 meter and mass of the string is 3 into 10 is 2 minus 2 kg. Answer the following. First is, does the function represent a traveling wave or a stationary wave? That means the given equation represents the stationary wave or the traveling wave. First we have to decide this thing. Second, interpret the wave as a superposition of two waves traveling in opposite direction. We have to also explain that there is a combination of or the superposition of the two waves traveling in opposite direction. And what is the wavelength, frequency and speed of each wave? After representing the two waves traveling in opposite direction, what should be the wavelength, frequency and speed of each wave? And last we have to find out the tension in a string. Clear this? Okay. So first the given equation is y is equal to 0.06. Now sine 2 pi by 3x into cos 120 pi into 2. Now this equation represents the stationary wave. Why? Because it is the product of the two harmonic functions. One is in terms of the x and second is in terms of y. It is, there is the answer part A. It is a stationary wave. Because it is a product of two harmonic functions. Two harmonic functions. One is in terms of position. X and other in terms of x, in terms of time t. Therefore, there is the stationary wave, not the traveling wave, because that's the form of this equation is in that form. Y is equal to 2a sin kx into cos omega t. Here the two functions are given, harmonic function, sine and cos. Sine is the function of position and cos is the function of time. There is the product of the two harmonic functions, therefore there is the stationary wave. Right. Now in B part, we have to find out what are the two waves. During the superposition of these two waves, we obtain this stationary wave. Clear? Therefore, the component of first thing we compare B. Then the equation number 1. Compare given equation with y is equal to our standard equation of the stationary wave 2a sin kx into cos omega t. Cos omega. Therefore, first the 2a is equal to 0.06. Therefore, 2a is equal to 0.06. Therefore, we obtain a is equal to 0.03 meter. Amplitude of the wave. Actually, the amplitude of the particle oscillating during the stationary wave is 0.03 meter. Now next, there is the key. K is equal to 2 pi by 3. 2 pi by. There is the wavelength. Right? But we know that the K is equal to 2 pi upon lambda. 2 pi upon lambda. Therefore, wavelength of the stationary wave, lambda is equal to 3 meter. Wavelength is 3. Now, comparing the omega. Therefore, omega is equal to 120 pi. But we know that omega is equal to 2 pi f. Therefore, 2 pi f is equal to 120 pi. Therefore, frequency f is equal to 60 hertz. Frequency is 60 hertz. So here we are going to discuss this thing. Interpret the wave as the superposition of the two waves traveling in opposite direction. What is the wavelength, frequency, and speed of each wave? So here we find out the wavelength and frequency. Now, what are the components of, or the equation of the two component waves in a given stationary wave? Now, equation of two waves, equation of two component wave in a given stationary wave. After knowing the value of the k and x, we know that y1 is equal to a sin omega t minus kx, and second is traveling in opposite direction, that means in positive x direction. That means the one is traveling in this direction, in positive x direction, while the second is traveling in opposite direction minus x. Both are the one-dimensional harmonic wave propagating along the positive and negative x axis, negative x direction respectively. Due to the superposition of these two waves, we obtain the stationary wave. So, in a given stationary wave R, first is y1 is equal to a sin omega t minus kx. Right? Substitute the value of a, omega, and t. That is the 0.03 sin. Omega is equal to what? 120 pi. Right? Therefore, sin 120 pi minus k. K we obtain 2 pi by 3 x. This is the one equation. And other is y2 is equal to minus a sin omega t plus kx. Plus kx. So it's equal to minus 0.03 sin 120 pi t. 120 pi t. Okay? Plus 2 pi by 3x. There is the other part of the other wave. Due to the superposition of y1 and y2, we obtain the given stationary wave. Now we are also interested to find out the speed of the each wave. The speed of the each wave. Therefore, we know that the v is equal to f lambda. V is equal to f lambda. F and lambda already we found f is equal to 60 into lambda 3 Therefore, 180 meter per second. That is the speed of both waves. Due to the superposition of these two waves, we obtain the given stationary wave. Now, C part. What is the tension in a string? For that purpose here, the transverse waves are given. Therefore, the speed of a transverse wave, or the velocity of a transverse wave is given by the equation V is equal to under root of T upon mu. But we know that mu is equal to M upon L mass per unit length. Therefore, V is equal to under root of T upon M upon L. L is taken in the numerator, so TL upon M. Now making the square on both sides. So we obtain that equation T is equal to mv square upon L. mv square upon L. Subtract the value of M and V and also L. So 0.03, that is the mass. Velocity is 180. 1 square upon length is 1.5 meter. Therefore, we obtain the 648 Newton. Tension is applied in a string. 648 Newton tension applied in a string to produce this stationary wave. Again, that is very numerical but quite lengthy, and here the concept of the theory must be clear so we can calculate it. For that purpose, the transverse displacement of a string tied at the both ends is given by yxt is equal to 0.06 sine 2 pi by 3x into cos 120 pi into t. So when the x and y are in meter, t is in second, length of the string is 1.5 meter, and mass of the string is 3 into 10 is to minus 2 kg. So in this situation, answer the following. First, does the function represent a traveling wave or a stationary wave? First, we have to do that, or we have to give the answer about that. This given equation represents the stationary or the traveling wave. So the given equation is this: y 0.06 sine 2 pi by 3x into cos 125 t. That is the equation 1. It is a stationary wave because it is a product of the two harmonic functions. One is in terms of the position x and other in position of time. So here the given equation is the product of the two harmonic functions. Therefore, it is a stationary wave. Clear this? So answer the first part. Now second, interpret the wave as a superposition of the two waves traveling in opposite direction. Also find what is the wavelength, frequency, and speed of each wave. So now we compare the given equation with given equation y is equal to 0.06 sine 2 pi by 3x into cos 125 with our standard equation of the stationary wave y is equal to 2a sine kx into cos omega. So 2a is equal to 0.06, therefore amplitude is 0.03 meter. Now this k is equal to 2 pi by 3, but k is equal to wave vector 2 pi upon lambda, so we can find out that lambda is equal to 3 meter. That is the wavelength. Now we are interested to find out the frequency. Therefore 125 is equal to omega. Omega is equal to 2 pi f. Therefore 2 pi f is equal to 125. Therefore frequency is 60 Hz. Now equation of the two component wave in a given stationary wave are one is traveling along the positive x direction, second is traveling along the negative x direction. So the component wave in a given stationary wave must be this form: y1 is equal to a sin omega t minus kx. Omega and k are known and a is also known. Therefore 0.03 sin 125t minus 2 pi by 3x. this wave propagating in positive x direction. Now in opposite direction, therefore y2 is equal to minus a sine omega t plus x. Actually, there is the reflected wave from the rigid support because this string is tied at the both ends. So there is the minus 0.03 sine 120 pi t plus 2 pi by 3. Already we found the wavelength and frequency. Now we have to find out the speed of each wave. Speed of each wave v is equal to f lambda. F and lambda are known, therefore 60 into 3, therefore 180 meter per second. Now third part, determine the tension in a string. So velocity of a tangent thread v is equal to under root of t upon mu, but the mu is equal to m upon l. Therefore, substitute the value mu as m upon l. Therefore, v is equal to under root of t l upon l. Now, making the square and equation in form t is equal to mv square upon l. Substitute the value of mass, speed, and length. We obtain the tension in a string is 648 Newton. Complete it. Here, this figure is not important only for your understanding, because in a stationary wave, due to the superposition of the two waves propagating in mutually opposite direction, the stationary patterns are formed like this. That is the second wave, and that is the first. Now the next 15.12. For the wave on a string described in example 15.11. Do all the points of the string oscillate with the same first frequency, phase, and amplitude. Explain it. And what is the amplitude of a point? Is a distance for 375 meters away from the one end. We have to also find out the amplitude of a point. Is it located at a distance for 375 meters from the origin of the one end. Now the given equation first we are down, because in this numerical we have to accept the equation of the stationary wave already present in numerical 15.11. Given equation yxt is equal to 0.06 sine 2 pi by 3x into cos 120 pi t. That is our given equation. Compare with our standard equation of the stationary wave. Y is equal to 2a sine kx cos omega. So we obtain the omega is equal to 120 pi. Therefore, 2 pi f is equal to 120 pi. Therefore, f is equal to 60 hertz. F is equal to 60 hertz. And this frequency is same for all the points, right, on the string, which is same for all the points of the string. All the points of the string. Right? Now, second is the phase of oscillation of all points on the string are also same, because all the points oscillate simultaneously and also perpendicular to the string. The phase of all points is also same. What is the reason? Because all points oscillate simultaneously and perpendicular to the string. perpendicular to the string. Right? So the frequency and also the phase of all the points of the string are same, but the amplitude are not same. Now, but amplitude of all points are not same. Right? It depends on position x. All points are not at the same position on the string. Distances are different. Therefore, the amplitude at x is equal to 0.375 meter distance. A is 2a sun 2 pi by 3x. Therefore, 2a is equal to 0.03 sun 2 pi by 3. X is equal to 0.375. That is the 0.06 sine pi by 2. Therefore, 0.06 into 0.7071. Therefore, 0.4243 meter. That is the amplitude of the oscillation at a point located at 0.375 meter distance from the one end. Again, the given equation yxt is equal to 0.06 sine 2 pi by 3x and cos 125. Compare this given equation with the standard equation of the stationary wave. Y is equal to 2a sine kx into cos omega t. Therefore, omega is equal to 125, thus the frequency is 60 Hz. So, which is the same for all points on a string. Now, the phase of all points on a string is also same, because all points oscillate simultaneously and perpendicular to the string. But the amplitude of the all points are not same because it depends on x. The amplitude at x is equal to 0.375 meter distance. A is 2a sine 2 pi by 3x. Substitute the value to a 0.03 sine 2 pi by 3 x is equal to 0.375. Thus, we obtain the amplitude at particular point is 0.4243 meter. Here this